I'm Adam from RFOXiA from our real lab. Today we are answering why putting multiple sensors on a shared I2C bus without dedicated addressing turns your data pipeline into a traffic accident. Enjoy our new soundtrack at the end of the video. Imagine you are in a room with 6 other engineers and there is one telephone. One telephone. No extensions, no hold button, no caller ID. Someone needs to report a temperature reading. Someone else needs to send gyroscope data. A third person has air quality numbers that cannot wait. They all pick up the phone at the same time. What you hear on the other end is not data. It is noise. That is I2C without address management. That is the problem this video is about. I2C is a two-wire serial communication protocol. It was designed by Philips in 1982 and it has aged remarkably well because the idea is genuinely elegant. You have two lines, SDA which carries data and SCL which carries the clock. Every device on the bus is either a controller or a target. The controller initiates transactions. The targets respond when called. Simple, clean, theoretically. The problem is that every device on an I2C bus needs a unique 7-bit address. That address is how the controller knows which sensor it is talking to. The controller puts an address on the bus and only the device that recognizes that address responds. Everyone else stays quiet. This works perfectly when every device has a different address. When two devices share the same address, the controller calls out that address and both devices respond simultaneously. Their signals overlap on the SDA line. The controller receives garbage. Your application receives garbage. And depending on how your firmware handles this, your entire system may lock up. Or worse, it may silently continue with corrupted data and you will not know until something very expensive behaves very strangely. This is not a theoretical concern. It is one of the most common hardware mistakes I see from developers who are new to multi-sensor design. They buy 4 sensors, wire them all to the same I2C bus, power everything up, and then spend 3 days debugging firmware that was never broken. The firmware was fine. The addressing was the problem. Now here is where it gets interesting. I2C addresses are not always fixed. Some chips allow you to configure the address by tying a hardware pin high or low. The same chip can live at x68 or x69 depending on how you wire it. This helps, but it does not fully solve the problem if you are building a dense sensor array with multiple chips of the same type, or if you are using chips from different manufacturers that happen to occupy the same default address space. And in a system with 7 sensors, the probability that 2 of them share a default address is not small. It is actually quite high. The conventional response to this is to either add I2C multiplexers, which are additional chips that let you switch between address spaces, or to use separate I2C buses entirely, which means more pins, more complexity, more firmware overhead. Both solutions work. Both solutions also add cost, board space, and design time. And both solutions exist because the developer did not plan the address map before they chose their components. The correct approach is to select your sensor ICs specifically for address compatibility before you lay out a single trace. This is a design decision, not a firmware decision. By the time you are writing code, the address conflicts either exist or they do not. You cannot fix them in software, you can only work around them, and every workaround adds complexity. On the MultiNav Pro Plus Sensors module, this decision was made at the component selection stage. 7 sensors, 7 distinct I2C addresses, no multiplexers, no address remapping, no additional wiring. The BMI270 from Bosch Sensotech handles the accelerometer and gyroscope functions and sits at its own address. The TMAGI5273 from Texas Instruments handles magnetometry at a separate address. The LPS22HH from ST Microelectronics handles air pressure at another. The MVH4003D from MEMS Vision handles humidity and temperature. The ZMOD45 TEL from Renesas handles air quality. 5 component families, 7 sensing axes, 1 I2C line, 0 collisions. This sounds simple. It is simple. That is the point. Simple, however, required careful work upfront. It required reading 7 datasheets and cross-referencing every possible default address before committing to a BOM. It required verifying that no 2 chips in the design occupy the same 7-bit space under any pin configuration. And it required understanding that the developers who will use this module should not have to think about any of that. They should be able to connect SDA and SCL, write a standard I2C read, and receive clean data from whichever sensor they need. The result is that all 7 sensors share one. So that is the addressing architecture. 7 sensors, 1 bus, no conflicts by design. Now let me show you the hardware itself. This is the complete sensor array on a single module. 7 sensing functions: accelerometer, gyroscope, magnetometer, temperature, air pressure, humidity, and air quality, all present, all independently addressable on one shared I2C line. No arbitration logic needed, no extra wiring, just clean organized data. Motion sensing and environmental sensing live on the same board without interfering with each other because they never share an address. The BMI270 handles motion at its own bus location. The pressure, humidity, temperature, and air quality sensors each occupy their own distinct address. The bus controller never has to guess which device is responding. These are the specific ICs chosen after mapping the full 7-bit I2C address space across all 7 functions. BMI270 from Bosch Sensor Tech, TMRG5273 from Texas Instruments, LPS22HH from ST Microelectronics, MVH4 Xiaozun 3D from MEMS Vision, ZMOD45110 from Renesas, each one selected partly for performance, partly for address compatibility with every other chip on this board. 1 I2C line, 7 addresses, 0 multiplexers. This is what the address-first design philosophy looks like in practice. You connect SDA and SCL, and the bus stays orderly because every device on it knows exactly when to speak and when to stay silent. That discipline is built into the hardware, not patched in firmware. 24 by 18 millimeters, that is the entire module. The compact footprint is possible partly because there are no multiplexer chips consuming board space. When your address map is clean from the start, you do not need extra silicon to manage the chaos that a bad address map would have created. Because the bus is collision-free, the data arriving from all 7 sensors in real time is trustworthy. Temperature readings are not corrupted by a simultaneous gyroscope response. Air quality data does not arrive with pressure values embedded in it. What you read is what the sensor measured, without noise from a neighbor that should have stayed quiet. Robotics, drones, environmental monitoring, wearables, field data nodes for the RFOXiA data network. Every one of these applications requires reliable multi-sensor data without bus conflicts. The addressing architecture on this module is what makes all of them possible without redesigning the sensor stack for each deployment. Temperature does not interrupt pressure. The gyroscope does not collide with the magnetometer. Air quality data arrives intact. The bus is calm, ordered, and entirely predictable. Not because anything clever is happening in firmware. Because the hardware was designed to make chaos structurally impossible. That is the distinction I want you to carry out of this video. Bus conflicts are a design problem. Dedicated address assignment is the design solution. The right time to solve it is before the schematic is drawn, not after the prototype stops responding.
Seven signals in the dark. Every axis, every arc, the pressure dropping overhead, the temperature that overhead, the temperature that fills with dread. I feel the tilt before you fall. I read the field behind the wall. The story that the data holds, the story that the data tells. I sense what you cannot see. Magnetic heat, motion locked humidity, motion locked in real-time streams. The world to code, not what it's. 7 sensors, one board, one truth. Every shift and every move, the invisible made visible now. The environment speaks, I know how. Ow. Gyroscope on the edge of flight. Accelerometer reads the night, equality through industrial air. 3-axis matter to wear. Humidity shifts before the storm. Pressure maps the rising norm. All 7 running, all in sync, faster than you stop to think. I sense what you cannot see. Magnetic heat, motion locked humidity, motion locked in real-time streams. The world to code, not what it's. 7 sensors, one board, one truth. Every shift and every move, the invisible made visible now. The environment speaks, I know how. Ow.